Okay, so in this particular section, we're going to be talking about properties of trig functions. So, let's talk about one of the properties of these 6 trig functions, known as an even or odd property. So, we have 6 trig functions, and some of them are considered even, and some of them are considered odd. And you're like, well, how do I know? Here's how we know. Let me draw this wonderful Cartesian grid that you have already been working with. And I am going to work with a 30-degree angle. Okay? I'm going to complete the triangle. Here's the right angle. Here's your 60-degree angle. Now, you know as well as I do, across from the smallest angle is the smallest side of 1. Across from the largest angle, which is 90 degrees, is the largest side, also known as the hypotenuse, or the radius of a circle, and that will be 2. And across from the medium side angle is square root of 3. And you're like, well, how do you know that? Go back and look at section 6.1 and 6.2 notes, and we talked about these special right triangles. Okay? Now, if I wanted to find the cosine of a 30-degree angle, cosine is going to be x over r. And if I look, my x value is the square root of 3. My r is 2. So the cosine of 30 degrees would be square root of 3 over 2. Good? Now I'm going to switch it up. Now I want to talk about an angle that's called a negative 30-degree angle, because now I went against the labeling into quadrant 4. I'm still going to complete the triangle, but now I'm in quadrant 4 to complete the triangle. This will still be considered a 60-degree angle. And the 60-degree angle isn't what you're concerned about being positive and negative. Remember, it's the central angle, the angle that's at the origin, that's either the positive or the negative angle. Okay? All right. So, across from the smallest angle of 30 degrees is the smallest side of 1. Across from the largest angle of 90 degrees is the hypotenuse, or the radius, and that will have a value of 2. And across from our 60-degree angle, which is the medium size angle, will still be the square root of 3. If I wanted to take the cosine of a negative 30-degree angle, I would have square root of 3, because that's my x value, over 2, which is the radius. Do you notice that the cosine of 30 degrees is exactly the same as the cosine of a negative 30 degrees? Because they are exactly the same, cosine is considered an even function, because the cosine of theta is exactly the same as the cosine of a negative theta. Good? Okay. Now, what happens, I'm going to leave these 2 triangles up here, and now I'm going to look at the sine of a 30-degree angle. Well, sine is y over r, and again, that was back in section 6.2. And my 30-degree angle is here, and the y value is 1, and the hypotenuse, the radius, is 2, so that's 1/2. Now, let's look at the sine of a negative 30-degree angle. Okay, so this is in quadrant 4, correct? And in quadrant 4, x is positive, but your y is, negative. So in this case, I would have a negative 1 over 2. So, sine is not an even function, is it? Because I didn't get the exact same numbers, did I? Therefore, sine would be considered an odd function, because the sine of theta would be equal to, now hear what I'm saying, would be equal to, taking the sine of theta and multiplying it by a -1. So we just simply write negative sine of theta. Because if I took this sine of 30 degrees and I multiplied it by a -1, what do I do to one side? I would have to do to the other, wouldn't I? Which is why it's written this way. So far, so good? Okay, now, remember something for me. What's the reciprocal of cosine? And if you're not sure, go back and look at section 6.2. No, the reciprocal of cosine is secant. Now, like, how do you remember that? I'll tell you in a second. If cosine is even, secant is also even. Which makes sense, because all you do is you flip it over, right? Okay. And what's the reciprocal of sine? That's right, cosecant. Now, like, how do you remember those so quickly? Here's what I remember, to be honest with you. Here's a little tidbit for you. Cosine starts with C, secant starts with S. Sine starts with S, cosecant start with C. I remember the C's and the S's go together. So if I'm talking about a C function, the S function is its reciprocal. So if I'm talking about a sine function, the reciprocal of sine, which starts with an S, would have to be a function that starts with a C, which would be cosecant. Does that make sense? Okay, let's talk about one last trig function. Yeah, you guessed it, tangent. So now I'm going to be talking about the tangent of 30 degrees. Now remember, tangent is the y over x. And again, look at section 6.2 to give you a hand. So I'm talking about 30 degrees, and the y value is 1. The x value is the square root of 3, which would make this 1 over square root of 3. And when you rationalize it, the tangent of 30 degrees is square root of 3 over 3. Remember, you have to rationalize. These guys cannot stay with a root in the denominator. And if I took a look at the tangent of a negative 30 degree angle, again, it's still y over x. And the negative 30 degrees, my y value is a -1. My x is a square root of 3. So I have -1 over square root of 3, which will rationalize to negative root 3 over 3. So, is the tangent of 30 degrees and the tangent of negative 30 degrees, are they exactly the same value? Yeah, no. Which means, would tangent be considered an even function or an odd function? Good, odd. So, tangent of theta would be exactly the same as the negative tangent of theta. By the way, what's the reciprocal of tangent? That's right, cotangent. So if tangent is an odd function, then so should cotangent be. Agreed? Okay. How are we doing? So far, so good? Makes sense? Love it. Okay. This is just nice little properties to remember for ourselves, because if they give me, say, the cosine of 45 degrees is 1, and they say, what is the cosine of negative 45 degrees? Well, you're like, well, wait a minute. If cosine is an even function, then the cosine of theta is equal to the cosine of negative theta, which means I automatically know this is also a 1. Good? Make sense? Okay, cool. Now, let's switch gears. I want to talk about some identities. And again, to speak about them, I'm going to draw this wonderful Cartesian system out here to give us a hand. And I kind of like my 30, 60, 90 triangle because it really does prove a good point. So here's my 30-degree angle, my 60-degree angle. Across from the smallest angle is the smallest side of 1. Across from the largest angle, which is 90 degrees, is 2. It's twice as much. And across from the medium-sized angle, which is 60 degrees, is that square root of 3. Now, I'm going to draw an additional Cartesian system. In this case, though, I'm going to have 60 degrees be my central angle, and 30 degrees be right there, and there's my 90-degree angle. So, again, smallest angle has the smallest side opposite, which is 1. The largest angle of 90 degrees has the 2 opposite, and 60 degrees, which is the medium size angle, has the medium side length. Now, here's what I want us to look at. I want us to notice if I take the cosine of a 30-degree angle, what would that be equal to? Remember, that's x over r. So that would be square root of 3 over 2. Got it. If I took the sine of a 30-degree angle, remember that's y over r, that would be 1 over square root of 2. Agreed? Good. Now, let me come down here to my 60-degree angle. If I took the cosine of 60 degrees, cosine, as we saw above, is x over r, which means I would have 1 over 2. And if I looked at the sine of 60 degrees, that would be y over r, like we stated above, which would mean it would be square root of 3 over 2. Agreed? All right. Now notice something. The cosine of 30 is exactly the same as the sine of 60, isn't it? And the sine of 30 is exactly the same as the cosine of 60, isn't it? Okay, that's going to lead to these identities here. But the one thing I need you to understand and notice right away is 30 degrees and 60 degrees. If I take these two angles and I add them together, they equal what? Yeah, 90 degrees. Okay, get back to geometry days. Do you remember what that word is called, what these angles are called when they add up to 90 degrees? If you don't, here it is. They're known as complementary angles. These identities we're going to write deal with complementary angles. Sorry. I'm having a little bit of a challenge. Oops. Okay. There we go. Complementary angles. So here's what that's telling me. Remember, the cosine of 30 degrees was exactly the same as the sine of 60, wasn't it? So if I take the cosine of an angle, it would be equal to the sine of its complement. If theta was 30 degrees, then 90 minus 30 would give you 60. And the sine of theta, because notice the sine of 30 degrees was the same as the cosine of 60. So if I take the sine of theta, it would be equal to the cosine of the complement. Does that make sense? Okay, so remember, the reciprocal angles are going to follow suit. What's the reciprocal of cosine? Yep, secant. So if I take the secant of theta, it's equivalent to me taking the cosecant of the complement, and then vice versa. And then last but not least is the tangent function. And the tangent of theta is equal to the cotangent of the complement and vice versa. Cool? Y'all with me on this? Okay, love it. Okay. Let's scoot on to a new topic, so to speak. Let me throw some examples at you. And they don't have to necessarily do with the identities we just worked with, because I gave you some examples on that. But I want to make sure you understand how to do these problems. So I would like to simplify. And I would like to simplify the sine of a 420 degree angle. Do you remember how many degrees are in a circle? Yeah, there is only 360 degrees in a circle. One circle rotation is equal to 360 degrees. By the word, that little word rot is a shorthand for rotation. But this is asking me to work with a 420 degree angle, which is more than one rotation of the circle, isn't it? Okay, so the question is by how much? How are you going to figure that out? How much is that over? Yeah, I think some of you are figuring that out. If I take 420 degrees and minus that one circle rotation, that leaves me with a 60 degree angle, doesn't it? What you're telling me is this. If I look at my Cartesian system, you're telling me that the 420 degree angle, which is one full rotation and then an additional 60 degrees, is the same as just a 60 degree angle because it ends up in that same spot. I make one full rotation and then I go 60 other degrees and it's exactly the same location. 60 degrees is the same location as a 420 degree angle. So if I want to figure out the sine of a 420 degree angle, basically I'm figuring out the sine of a 60 degree angle because they end up in the same location. So remember that 60 degree angle. Finish your triangle off, right? Finish that triangle. There's your right angle, which means there's your hypotenuse. Across from the 60 is square root of 3, and that's supposed to be a 30 degree angle right there. Which means sine is what over what again? Yep, sine would be y over x, which means you would end up with, whoops, sorry, not y over x. See, this is why I have you guys do it with me. Y over r, which means I have the square root of 3 over 2. Cool? Does that make sense to you? Okay, let me give you another example. 13 pi over 6. You're like, that's not degrees. You're right, that's not degrees. That's radians, isn't it? Okay, so you have to remember how many radians one full rotation of the circle has. Go ahead, I'm waiting. Gives me time to write this. One circle rotation in radians is, yeah, 2 pi. Which means, but that has a denominator of 6, the original problem, doesn't it? Okay, so for those of us who are visual people, let's change it. If I took 2 pi and made it a fraction over 1, and I wanted to make it have the same denominator as my original fraction, I'm going to have a denominator of 6. I'm going to have to multiply top and bottom, right? Which gives me 12 pi over 6, doesn't it? Got it. Which means one full circle rotation is 2 pi, which is equivalent to 12 pi over 6. So, let me, right? Here's our Cartesian system. So this is for problem number 2. This was problem number 1. That means I'm going one full rotation around the circle, 12 pi over 6, or 2 pi, whichever you want to call it, because they mean the same thing. Now the question is, how much is left over? Right? I had 13 pi over 6 to start with, and I'm taking away 12 pi over 6, which leaves you, that's right, 1 pi over 6. And remember from section 6.2, 1 pi over 6 is a first quadrant angle. So what we're being told is I'm going one full rotation around the circle and then a little bit extra. And that little bit extra is pi over 6. So basically, it's a first quadrant angle I'm dealing with, isn't it? Okay, so you're like, pi over 6, how many degrees is that? Well, if you look back what we did in section 6.2, or actually section 6.1, we converted, right? If you want to know how many degrees this is, you use this conversion. I do some canceling, and I end up with this being a 30-degree angle. Pi over 6 is equivalent to a 30-degree angle. So, and by the way, I remember, since pi over 6 is 30 degrees, I remember then that pi over 3 is 60 degrees. And you're like, how do you remember that so fast without doing a conversion? Well, remember I told you about the C's and the S's going together with cosine and secant being its reciprocal and sine and cosecant being its reciprocal? Well, I do the same thing here. My 6's and my 3's go together. And that's my little way of remembering what pi over 6 is equivalent to and what pi over 3 is equivalent to. Okay, so let's finish this triangle off. So I have got this triangle that I am working with. Oops, sorry. Can't go beyond that circle. So I've got this triangle I'm working with. I know pi over 6 is a 30-degree angle. And across from the 30-degree angle is a 1. Hypotenuse is 2, which makes this the square root of 3 down here. And if I am looking for the tangent of, in this case, pi over 6, which is still a 30-degree angle, I am going to take, what again? That's right, y over x. So my y is 1. My x is the square root of 3. I need to rationalize, which means the tangent would give me, pi over 6 would be square root of 3 over 3, which means that's actually the tangent of 13 pi over 6. And let me back up on problem number 1. That sine of 60 degrees being square root of 3 over 2, that means the sine of 420 degrees is also square root of 3 over 2. Cool? So far so good? You guys with me? Okay, loving it. Let's work on this problem. to give you the sine of theta being equal to negative 24 over 25. And I want you to find the other 5 trig functions. Okay, so the question is, what do we know? Well, we know the sine of theta is equal to, oops, sorry about that, guys. The sine of theta is equal to the opposite over the hypotenuse, right? Or if you're on the grid system, it is going to be y over r. Agreed? Now, you're like, well, how do I know which one I'm on? Because they actually put in a negative here, I know that I am dealing with a y value because they put it on the grid system. They took this sine, and because they told me my top number was a negative number, that means I am working with the negative y-axis. Opposites, they're not positive or negative. They are just a standalone triangle with nothing to do. If I talk about opposite, there's opposite. If I talk about hypotenuse, there's hypotenuse. And there's adjacent. They don't have any signs attached to them. As soon as they start throwing negative signs at me, especially, I know I'm on a grid system. So, let's take a look at this. So, I know that y is equal to negative 24 and r is equal to 25, which means in order to complete this, we need to find the value for x. Okay, remember, regardless if it's on the grid system or if it's a standalone triangle, this is still a right triangle that we are working with. And if it's a right triangle, then we still have to remember to deal with Pythagorean's theorem. He never goes away in trig, which is to our great benefit. And x squared plus y squared equals r squared. Remember, things changed up a little bit. Instead of a, b's, and c's, which is what this triangle would have. This triangle would have a, b's, and c's, but the grid system has x, y's, and r's. All right? So I'm looking for the x. I got the y. I got the r. You do all the work, and you got x is equal to either a positive 7 or a negative 7, don't you? Now, here's the deal. If they don't tell me which quadrant we're in, because did they tell me a quadrant? No. Then I am going to always go with a positive x. They need to tell me a quadrant if they want me to use the negative x. So, the x value we're using is positive 7. Cool? Alrighty then. Are you ready to write your trig functions? Okay, let's see. The cosine of theta. Cosine is which variable over which variable? That's right, x over r, which would give us 7 over 25. Sine they already gave us, so that was very nice of them. And tangent, how do you find tangent again? Yeah, tangent is y over x, which would just be negative 24 over 7. Since I have these, it's easy for me to find their reciprocals. What's the reciprocal of cosine? That's right. Starts with an S. That's secant, which means all I have to do is flip that over. What's the reciprocal of sine? That's right. Starts with a C. That's cosecant, which means all I have to do is flip this over. And last but not least, the tangent and cotangent, they're kind of the easiest ones to remember who's the reciprocal of who. And there are my other 5 trig functions. Good? All right. I got one last set of problems for us. I want us to identify the quadrant. Here's what I'm given. I'm given that the sine of theta is less than 0 and the tangent of theta is greater than 0. And they want me to tell them which quadrant that's in. Okay, so remember, if it's less than 0, then that means that this will be a negative, won't it? And if it's greater than 0, that means this would be a positive, wouldn't it? Okay, so question for you. Which quadrant is sine positive? Remember, that deals with the y's. Y's are positive in which quadrant? Good. 1 and 2. Gotcha. Tangent. Tangent deals with which variables again? That's right, x's and y's, right? Y over x, it's x's and y's, right? And I need tangent to be positive, which means both x and y need to be positive, good, or x and y both need to be, yeah, they could both be negative, because 2 negatives will give me that positive, won't it? Okay, so which quadrants are we talking about here? Yeah, quadrant 1 for sure, because both x and y are positive there, but I'm also talking about quadrant 3, because x and y are both negative there, which will still give me a positive tangent, right? Okay, so I'm trying to identify the quadrant. Which quadrant has the sine of theta being less than 0 and the tangent of theta being greater than 0? Which quadrant has both of those requirements met? If you notice, that would have to be quadrant 1 because that's the quadrant they both have in common. Cool? Okay, let's take a look at this then. Got another problem for you to work on. And in this one, I have the cosine of theta being greater than 0, and I have got the cotangent of theta being less than 0. Okay, so same thing, let's check it out. Cosine is greater than 0, that means this has to be positive, doesn't it? And cotangent less than 0 means this has to be negative, agreed? Okay, so if cosine is positive, which quadrants are we talking about? Remember, cosine deals with those x's, right? Because it's x over r, but r is always positive because the radius is always positive. X being positive in quadrants 1 and, yep, 4. And if I'm looking at cotangent, cotangent deals with x's and y's, doesn't it? But if it's negative, I got one of each, don't I? One negative and one positive, because that's the only way, isn't it? Whereas over here in problem 1, both x and y had to be positive, or both x and y had to be negative. So, which quadrants have one of these being positive and one of these being negative? Yeah, quadrant 2 for sure, and quadrant 4. Excellent. So which quadrant has the cosine of theta being positive and at the same time the cotangent being negative? That's right. Notice they both have that quadrant 4 in common. So in this case, the answer is quadrant 4. Whoops. That's a pretty funky looking 4, isn't it? There we go. Awesome. Good. Y'all with me? Loving it. Okay, so you guys have fun with homework, and I shall catch you on the flip side. Bye.